Welcome to my channel AI Basics with AK. Here we are with another new episode on Introduction to Statistics of Season 3, and the topic is Episode 7, Central Limit Theorem. In Episode 5, we have seen that a sample space is a set of all possible outcomes. An event E is a subset of a sample space. An outcome is a single result. Like say for example, if we are throwing a dice, what is the number of possible outcomes? Okay, the number of possible outcomes is 6. Say for example, if we are rolling 2 dice, what is the number of possible outcomes? It can have 36 possible outcomes ideally. Isn't it so? Just nothing but 6 into 6. Now, what is an event? Say for example, if we want to predict an event where when we are rolling 2 dice, the sum is 3 when we add the 2 faces of the dice. That's an event, which is a subset of a sample space. What is an outcome? Ideally, if it is a 3, it can be either 1, 2 or 2, 1. If we have an numbering section, okay, this is dice 1 and dice 2. In that case, okay, either of them ideally is an event, and outcome can be only one, either this or this one. Now, having this understanding, we move to episode 6 that, okay, we have just rolled it once. There is just a single phase. Okay, what happens if we roll it many times? Because the pattern is the same, because when we roll it, if we have rolled it, okay, if it is only one dice, what is the probability that any number can come? It can be 1, 2, 3, 4, 5, and 6. So the probability remains 1 upon 6 because you can get only one phase out of 6 possibilities. And it's very uniform, right? Be how many number of times you roll, the probability doesn't change. So that's what we have seen it in the last time, like say, for example, if we roll for 10, okay, we see a little bit non-uniform distribution because 5 can occur many times and maybe 3 can occur many times, but not 2 and 4. But if we roll it enough times, like 500 rolls or 1000 times, okay, we can see that, okay, each phase has an equal probability to occur. This is what further we have deep delved that, okay, there are 3 distributions, which is uniform, normal, and binomial. Uniform is nothing but where all outcomes occur equally. And what is a normal or a continuous distribution ideally? Which it means that if we have an exam score, okay, it's not always the same. It can happen in any distribution. Okay, here we have made him new normal because that's like a normal distribution. Like say for example, few people will be less height and there will be more number of people with of same height, and then there are more people with more height ideally, right? That's what we can see it out. This becomes a little bit like a distribution. Why it is called as a normal distribution, we will discuss more right now in the current section. Ideally, if we plot it out as a height, okay, as the number of students, ideally it will be like this. Maybe it will be lesser height and then the same height and then the more height. But what is a normal distribution is what we will discuss right now in the current pattern. Binomial distribution is nothing but it is like a coin flips, like the count of success and failures. Now, what we have done is that, okay, even if we change, say for example, if it is a normal distribution, this just assume that, okay, the normal distribution looks like a bell curve. And uniform distribution is like a uniform distribution. And a binomial distribution, it has peaks and lows. So here, be any number roles which make it, okay, the distributions does not change. Even, okay, even if the n is equal to 1000 or 5000, the distribution does not change. So what would we so far? We saw uniform distributions, we saw binomial distributions, we saw normal distributions in general in the previous example. And what we have seen is that if the data is uniform, it stayed uniform. If the data is skewed, it stays skewed, or in generally, let's call it as a normal. And even if we take more samples, the population distribution does not change. So we would have learned it like in bits and pieces. Most of the people would be speaking about normal distribution. So this is more important that, okay, uniform data does not magically become normal. This is very critical before we understand what central limit theorem. Why? Because population, okay, is the whole truth data. Sample is only what we observe, like what we collect. Statistics is the summarization. The statistics is nothing but like mean, median, mode, sum, average scores, loss, etc., etc., etc. So in practice, do we see the full population? Ideally, no. We only rely on sample, and most often we rely on sample-based summaries. So what do we rely on? We rely on aggregates, not on raw observations. This is very crucial in understanding. So when we have seen it here, the uniform remains the uniform, but ideally we do not know whether we would be plotting. Ideally, if there are 100 variables that we want to see it, do we see all patterns for 100 variables? Might not be. So we heavily rely on the central tendency metrics for most of the business decisions. So CLT is not about data, it is a statistics. It is not about individual data points, it is about the distribution of the mean. This is very important. Ideally, we are discussing here a distribution of the mean. So let me tell you very clearly. Now, this is a whole population, right? And here, say for example, here we will take a sample. From the sample, we will get one mean, say sample 1. And one more sample we will take here. And here we will say that, okay, this sample mean 2. And etc., etc., etc. When we collect these different samples and plot them, we will see that, okay, it has this beautiful normal distributions where most of the samples have a nearest mean, and then there are few outliers, and here like that. So when we collect these samples from a larger population, this population can be your uniform, okay, or any other distributions. But when we take the samples of these distributions and we calculate these means and we plot them, we see a normal distribution. This is what a central limit theorem is. If we take independent samples from any distributions with finite variance, then the distribution of sample means become approximately normal as as the sample size increases. This is the most crucial one. We cannot take one sample. There is a metric that, okay, what is the right sample that we can take such that we can assume that that we can use the methods of a Gaussian distribution, because once we approximate to a Gaussian distribution, the statistical computations becomes much more easier, because be it be any distribution, we can follow just one rule. Say for example here, okay, this is just a computation of a mean here. I'm just drawing a mean of one distribution. When it is just one, when we take only one sample, you don't see a very clear, we see a uniform distribution, because the sample mean might be same. But when we increase it, slowly we are seeing some kind of a bell curve. As we increase it, okay, the bell curve really smooths like this. And this is nothing, this is as simple as that, how CLT changes the behavior when we are taking the aggregates of samples. And when the sample sizes are large enough, like here you have seen it here, when n is equal to 100, you can see that it's merging into a normal distribution. So just keep it in mind, which is very basic, what CLT doesn't say. It never discussed about population. It never discussed about individual observations. It never claimed about reality. But what it does is that once we have, it gives you a modeling comfort, which is most crucial for regression and all other statistical methods that we will be using. Because we can model means it is a Gaussian, we can simply use a Gaussian methods, and we can use confidence intervals very comfortably. More importantly, we don't know about population, but if we have an enough sample, we can quantify that uncertainty, because we don't know about reality, right? Reality of the population, we don't know. It can be any distribution. But once we have a sample, a good enough sample, we can quantify that uncertainty, because we can assume that the distribution is a sample distribution. Okay, the averages of the distribution tends to be a normal. So once we have this comfort, even though the underlying structure is different, it becomes very easy to quantify that uncertainty and reason mathematically. Beautiful, right? So the Gaussian, let's me reiterate here, okay, because it's most important. Gaussian is the shape of an aggregation. Got it? And since the reality is messy, statistics is structure. Reality is messy, irregular, and unsymmetric. But statistics is summarize averages and aggregates. So what happens when we summarize aggregates and everything? It reduces the noise. When we take that reduction in noise, the messy reality becomes a clean statistical behavior. I'll give an example. Say, for example, you have a large data, so many points like this, and we have very high outliers. The moment we take statistical averages, we are representing all this behavior with a one number, right? So we are trying to reduce the huge noise to a one number, and assume that we have taken those numbers multiple, we have multiple samples kind of a thing. Then what happens is that we are reducing the real world messiness into a little bit more predictable statistical behavior. That's what CLT gives us, that comfort. Okay, whatever the distribution is, you have enough samples, let's use Gaussian, and that's the comfort that we can have it. This is a very beautiful discovery, ideally in a statistical world, which actually solved many problems. So when CLT can mislead you, this is nothing but, okay, we know that this gives you a huge comfort, but if it is heavy-tailed and strong dependence exists between the variables, and the sample size is small, most importantly, you care about extremes. It means you care about outliers but not averages. Then this might mislead you ideally. So Gaussian comfort should not be equated to a guaranteed safety. Beautiful, right? So see you in the next episode. But I just want to leave you with one thought with this slide, because I have said you that CLT can mislead you. Maybe in future seasons, I'll discuss you one thing, why n is equal to 30 is a myth, especially in a business and an ML world, and why at times CLT fails of one reason, most importantly, when we care about extremes but not about averages. We'll discuss more, but at this point of time, absorb, okay, there is a very beautiful theorem where it gives us a comfort that, okay, you don't know about population, we have a huge uncertainty in the population, but you have enough sample. Most probably the people say is n is equal to 30. You have 30 samples, then you can approximate this distribution into a normal distribution and can apply Gaussian methodology. So this gives us huge comfort for us. That's it, and see you in the next episode. Thank you.